All right, so in ammonia, we have sp3 hybrid orbitals as well. So that's because our electron configuration of ammonia, or at least the valence electron configuration, has these two s electrons paired up, and we've got three 3s electron, or 2s, sorry, three 2p, there we go, that's what I meant, three 2p electrons that are unpaired, and we are going to use those three unpaired 2p electrons to bond, but we want all of our orbitals around nitrogen to have the same energy. So even though we don't need to hybridize, or we don't need to promote any electrons um, in order to get unpaired electrons for this case, we do still want to hybridize so that we can have these all be equal energy orbitals. So we take, again, the 2s and 2p orbitals. So we have one 2s orbital and three 2p orbitals. So that's going to give us s and p3, so sp3 hybrid orbitals. But in this case, we have one of those sp3 hybrid orbitals does not contain unpaired electrons. It has two paired up electrons. And that fourth sp3 hybrid orbital that has the paired electrons, that's going to be what gives us our lone pair on nitrogen. The other sp3 hybrid orbitals are the ones that are going to overlap with the hydrogens, the hydrogen 1s orbitals, to form these bonds. So the sp3 orbital accommodates, one sp3 orbital accommodates the lone pair of electrons, and then the other sp3 orbitals bond with the hydrogen 1s orbitals. Okay, so even though there are not four bonds, we do still have four hybrid orbitals. So nitrogen is still sp3 hybridized because, and you can always tell that because of the number of electron domains. There's four electron domains. It's got a tetrahedral electron domain geometry, so it is sp3 hybridized even though it's only got three bonds. All right, so we can see similar things with methanol. So methanol, or CH3OH, also has sp3 hybridization. So on carbon, just like in methane, has four sp3 orbitals, and three of those are overlapping with the hydrogen 1s orbitals to give us those CH bonds, and the other one is overlapping with the oxygen sp3 orbital to form the carbon-oxygen bond. So those are our four hybrid orbitals for carbon, and oxygen also has sp3 orbitals. So you can tell by looking at the electron domains. There are four electron domains. So there's the two bonds, and then there's two lone pairs. So in oxygen, our electron configuration is this 2s, and then we've got another pair in the 2p orbitals. So now we only have two unpaired electrons to form bonds, but all of the orbitals on oxygen are going to be the same energy, so that our bonds and our lone pairs are all equally distributed. They wouldn't be equally distributed if they weren't all the same energy. So we need to hybridize. Even though we have only got two unpaired electrons to make bonds, we still hybridize and make sp3 orbitals. So two of those sp3 orbitals are filled, and they are lone pairs. And then the other two sp3 orbitals on oxygen have unpaired electrons, and that's what forms this carbon-oxygen bond and this oxygen-hydrogen bond. So we've got our sp3 orbitals on carbon. There's four of them, making four bonds. And we've got four sp3 orbitals on oxygen. Two of them are making bonds, and two of them are lone pairs. So again, Count the electron domains, not the bonds, to see the hybridization. All right, we can keep going with hybridization to talk about these expanded octet central atoms. So there is a bit of controversy. Some people don't agree that, they don't agree that d orbitals can participate in hybridization because d orbitals are high in energy, so they are not likely to mix with the lower energy s and p orbitals and form hybrid orbitals. But we're going to use these d orbitals to discuss uh, or to form some hybrid orbitals, which help us discuss the geometry of these expanded octet central atoms. Even if we're not sure that this is what actually happens, it helps us explain it. So that's what we're going to stick with. So molecules with 10 electrons assigned to the central atom have sp3d hybrid orbitals forming their bonds. So, for example, pf5 or PCl5, same difference. Phosphorus has 5 electron domains and forms 5 hybrid orbitals. So this is our electron configuration for phosphorus to start with. We have, it's just like nitrogen, we have 3 unpaired electrons in the p orbitals and 2 paired up electrons in the s orbitals. So now, instead of just having one of our orbitals have a pair of electrons like it did for nitrogen in the ammonia molecule, now instead phosphorus can access the d orbitals. So phosphorus is in the third period, so it can access the 3d orbitals. So we can promote one of those paired s electrons to the d orbital. So now we have 5 unpaired electrons and we hybridize those orbitals. So we mix the 3s, 3p, and 3d orbitals and make sp3d hybrid orbitals. So we took one s orbital, 3p orbitals, and one d orbital. So we don't use our superscripts of 1, so we just have s and d, but we do use our superscript for the p orbitals, so there's 3 of those, so it's sp3d hybrid orbitals. And again, that's because 1 part s, 3 parts p, 1 part d atomic orbitals. And these 5 hybrid orbitals point to the corners of a trigonal bipyramid. So that's this trigonal bipyramid. That's where we get our trigonal bipyramidal shape. So it's kind of hard to see on here, but this one's kind of going in that direction. This one's going this way. This one's going this way. Those are our equatorial hybrid orbitals to form our equatorial bonds. And these two are our axial ones. So this is where we get our trigonal bipyramidal shape of phosphorus phosphorus pentafluoride or pentachloride, same difference. Molecules with 12 electrons assigned to the central atom have sp3d2 hybrid orbitals to form their bonds. So sulfur, just like oxygen, has this electron configuration that has paired up electrons in the s orbital, 1 pair of electrons in the p orbital, and 2 unpaired electrons in the p orbitals. But unlike oxygen, sulfur can access the 3d orbitals, so we can promote those paired up electrons to the 3d orbitals and have 6 unpaired electrons to form 6 bonds. So now we're mixing 6 atomic orbitals and making 6 hybrid orbitals. And these are called sp3d2 hybrid orbitals because we have 1 part s, 3 parts p, and 2 parts d atomic orbitals. And these 6 sp3d2 hybrid orbitals point to the corners of an octahedron. So here's our octahedral shape of our hybrid orbitals. And if we want to have a good time, we can add our fluorine orbitals to show this overlap that happens here. So it gets real messy because fluorine also has a bunch of p orbitals that are doing the overlapping. So we have this octahedral sulfur set of sulfur hybrid orbitals overlapping with the um, fluorine p orbitals to form this octahedral molecule. So it looks a little funny, but that is how the bonding works and the hybridization of sulfur atoms. So here's a little summary for you guys. For hybridization, you want to look at the number of electron domains to see how many hybrid orbitals you're going to have and what kind. So if there are 2 electron domains, we have a linear molecule. And we have 2 electron domains, so we need 2 hybrid orbitals. So we're going to take one one s orbital, one p orbital, hybridize them to create 2 sp orbitals. If we have 3 electron domains, we've got a trigonal planar molecule. So we're going to take one s electron and one s orbital and 2 p orbitals, mix them together and form 3 sp2 hybridized orbitals or hybrid orbitals. If we have 4 electron domains, we're tetrahedral. We have 1s and 3p orbitals that we're mixing together, atomic orbitals that we're mixing together to form 4 sp3 hybrid orbitals. If we have 5 electron domains or 6, then we have trigonal bipyramidal or octahedral molecules, and we're taking 1s orbital, 3p orbitals, and 1 or 2 d orbitals, and forming these 5 sp3d hybrid orbitals or 6 sp3d2 hybrid orbitals. So this table will be really helpful for you guys to try and remember the hybridization of different electron domain geometries. And I'm going to stop here and start another video.